Hi class, in this video we're going to talk about problems 4, technically 5 and 6. Okay, so here's the basic idea. We're going to be talking about a t-distribution which is very similar to the normal distribution. Now let me give you a sketch to scale, and in this case I'm attempting to show both of the distributions using Desmos, and here's what they look like. Okay. So give me just a second so I can expand it. Okay, here you're looking at the two main graphs. The red one happens to be the normal distribution, and then the blue one happens to be the t-distribution. Now, we use the t-distribution when we have small samples or data that's approximately bell-shaped, and the idea is that we may carry a little bit of error, and for some of the problems it may be more accurate to use an approximation to the normal distribution, which happens to be the t-distribution. Now, what you're going to see here is as n becomes large, because typically the scenario is that you have small values for n, and n represents the size of the sample, you're going to see that both of the actual distributions happen to be about the same. Meaning we use it to try to get a bound on the error, and this is when data is either not perfectly bell-shaped, or there are some concerns about the data being bell-shaped. So as opposed to using the normal distribution as an estimator, we use the t-distribution, and that helps us account for the error. Now let me go back to the handout. Okay, so let's start talking about problem 4. Now in problem 4, we're told that the actual distribution happens to be t-distribution, and they're asking us to find a specific value. Here we're told that in this case the total area to the left of this t-value happens to be 0.20. Now remember that for any of the distributions, they represent population, so therefore total area under the curve is equal to 1. So that means that if below this actual t-value you have 0.20, that means that above you're gonna have 0.80. Now let me move to the emulator so I can run the code and show you how we run this specific type of problem on the calculator. Okay, the proper code is gonna be here. We're gonna do second and technically distribution, and then we're looking for inverse t. And give me a minute so I can actually run the whole command. Okay, and then this specific problem has a total area. Give me a minute because I moved the actual table. Okay, it has a total area of 0.20. So the command for most of the calculators, this is area to the left, so that's going to be 0.20. And then degrees of freedom, it's always n minus 1. So the total size is equal to 30. So that means we're going to have a total of 29. And then for most of the calculators, this is how you're running it. Let me pause the video so we can go back to the command. Okay, I posted the answer here. And in this case, to run it, well, after we run it, we're told that, well, this critical value that has 0.20 area to the left with n minus 1, that would be the degrees of freedom, or in this case 29, happens to be negative 0.85. So let me type it up and then I'll go back to the calculator. So all critical values are going to be expressed to 2 decimal places, so negative 0.85. It doesn't, yes, I do have the negative there. Now let me go back to the calculator to show you how to run it again. Okay, so once again, you're going to hit second in distributions. You're going to activate, in this case, the t-distribution. It saved the command, so area to the left, and this is always for area to the left is 29. The size of the sample is 30, so the formula for degrees of freedom is n minus 1 or 29, and then you simply paste it. This in the calculator represents area to the right. So in this case, that's going to be technically 0.20, which gives us the negative 0.85. Now let me go back to the assignment. Once again, total area under the curve for any distribution is 1. And then this one wants a t-value that has a 0.20 area to the left. Now, let me move to problem 5. On problem 5, the explanation of the settings is a little bit different. You're told that the area to the distribution is 0.10, so that's this part here. And then total size is equal to 51. So that means degrees of freedom is going to be 50. Now, this portion here, what you enter on the calculator, it's always area to the left. So that means that the calculator for most of the commands, it's going to have area to the left. Yours is going to be similar. Some calculators allows you to put area to the left or to the right. So you may have to enter 0.10. Please run it, but in this case, you're running the same command and just adjusting. I'm getting that the t-value happens to be technically 1.30. Since in case we round to 2 decimal places, that's going to be, well, technically 1.3. Once again, the calculator, you're entering area to the left. Let me run it just so that we can confirm. So let me pause the video and go to the calculator. Okay, so once again, to run this one, second distributions, and then go to inverse t. You have 0.90 area to the left. Degrees of freedom, it's going to be 50. And then that's going to give us the 1.3. Sometimes the software is going to want more values, typically rounding to 2 decimal places, so that's why I rounded it to 3. Okay, let me go back to the third example. And the third example, which happens to be example 6 for this video, this one, it's actually a little bit tricky because they're calling the area on both tails, and that's this tail and that tail, totals 0.30. So that means that in order to get the area on one tail and to use the same command, for some of your calculators, you can actually input 0.30 on both tails, but not this particular one. In that case, you would have to divide it by 2, which is 0.15. And that means that on both tails, you have a total of 0.15. And in this case, you're using inverse t 0.15 with 30 degrees of freedom, 1 less than n. And that's going to give us that the t value is equals, you can write it as approximately, that would be perfectly fine, 1.005 would be fine. And t is equal to, so this one should be a negative, and this is a positive, so 1.05. Now, this particular one, because it has area on both tails, you provide both of them. And notice that as we compare to the previous one was only concerned on area above, and then the very first one, which is example 4, area below. So this one's a little bit tricky. Even though they're calling a critical value, because they're mentioned both tails, that means that we have to provide both of these. Now, just to give you a little bit of a perspective of what you're going to see later on, and in later problems, we're finding these values. And within those values, that's going to be accounting for the error on a specific estimate for a confidence interval or for a hypothesis test. At the moment, we're just looking at a distribution. We know what n is, but in this case, this 1.05 is going to help us bound the error and get a better estimate. That's actually it for these two. Now, if you see that you don't have the same commands at that point, we have to go to the tutoring center or email me to make an appointment. That there's a chance that your calculator is slightly different. So this one, you're running the same commands except that you're putting 0.15 and it's only going to give you the negative. You have to use symmetry, and then technically you're going to have both of those or both of the values on both ends. For all of these, we technically have the critical value only on one end, as an example 4, Then on example 5 on one end, but this one, because they mention both tails, that means that we have to actually provide these two. The last thing I'm going to do is I'm going to label these two and then upload the solution to the Canvas shell. At the moment, I have to pause the video, but we do label the actual axis with the proper value once we find it, and then provide some sort of a sentence. That's actually it for the video.